Hello everyone, welcome back. In this video, we'll be discussing about the first and the third problem of today's weekly contest. Find the number of good pairs 1 and find the number of good pairs 2. Both the problems are exactly same. The only difference lies in the constraint. If we have solved this, we'll be discussing two different approaches to this problem. One by going over all the factors, second by going over all the multiples. If you have solved this problem with one of the approaches during or after the contest, I would still encourage you to watch and understand the second approach as well, because both the approaches comes handy while solving these kind of problems in general. And if you're not able to code this entire thing during the contest, I'm very sure after watching this video you will be able to learn few new things which you can apply in general to any problems in future of this kind for sure. So with that, let's get started. The problem states that you are given two integer arrays nums1 and nums2 of length n and m and a positive integer k. A pair is called good if nums1 of I is divisible by nums2 of j cross k, and you return the total number of good pairs. So let's take an example. Let's say nums1 is 1, 2, 4, 12 and nums2 is 2 and 4 and k is 3. So we want to figure out how many pairs are there such that nums1 of I is divisible by 3 into nums2 of j, right? So let's assume that j is 0, right? We have to figure out how many nums1 of I are there which is divisible by nums2 of 0 cross k, which is 2 cross 3, which is 6. So we have to figure out how many of these numbers are there which are divisible by 6, and answer is just 12. So 12 is the only one that can divide 6. Rest numbers can't divide 6. So overall we got one possible pair which is 3, 0 for j equals 0. Similarly, for j equals 1, you want how many numbers are there or how many i's are there such that nums1 of I is divisible by 4 cross 3, which is 12. Again, there is just one such number which is 12 itself. So again 3, 1 is one such valid pair with j equals 1. So there are only two possible valid pairs and hence answer here is 2. So hope the problem statement is clear. Now for simplicity, let's forget about k completely. Let's assume that k is 1 and we will solve the entire problem with both the approaches with k equals 1 only, and adding k to that will be very trivial after you have understand how to solve this without k, right? So for the long section of the video will be focused on solving this problem without k, and after that you will have one more opportunity to pause and try to think about yourself, try to think about the problem, how you will solve this without when k is not equals to 1, right? So with that, what is the brute force solution to solve the problem with k equals 1? Obviously, so one of the brute force way would be go over all possible pairs, figure out which one of them are valid and just count that into your answer. So in other words, for this I you will try out all possible j. For each I and j you will figure out whether it is a valid pair or not. How to figure out that? Simply check whether 2 is divisible by 6 or not. In this case 2 is not, so you will not count this as one of the valid pair, whereas if you get this, then this is a valid pair because 2 is divisible by 1, right? So you will go over all possible pair, figure out how many of them are valid, and that will be your answer. So what will be the time complexity? Time complexity will simply be you are going over all possible pair, which is n into m pairs, and for each of them you are figuring out whether they are valid or not, and that you can simply do using a modulus operator. So that is like order 1 operation. So let's forget about this. So overall complexity is order n cross m, and this will pass this first question easily because n and m are both 50. But you can't afford this for the third problem where n and m are 10 power 5. So you need to optimize this, and notice both n and m are 10 power 5. So you either have to remove n or you have to remove m, and both is possible. and that's where we have two different solutions to this problem. So let's first try to avoid m, right? In other words, if you are trying to avoid m, you are saying that you don't have the liberty to go over all possible j, right? You are still going over all possible I, that is there, but you can't go over all possible j. In other words, for a particular I, let's say for this I, you want how many valid j's are there in less than order n time. And why how many? Because you just care about the count, you don't care about the actual pairs, right? So if you can figure out the count of valid j's for this I efficiently in less than order m time, you should be able to solve this, right? Now what does this mean? For this I, you want all possible j which are valid. So in other words, you want all the numbers like with which 9 is divisible by, right? So 9 is divisible by its all the factors, right? So all possible factors of 9 is 1, 3, 9. So what you want is, I want how many 1s are there, how many 3s are there, how many 9s are there. And if you can figure this entire thing out efficiently, like you can figure out how many factors of 9 are there in this entire array efficiently, we can reduce this order m to some smaller number, and that will solve the problem for the given constraint. The other approach is, okay, I will iterate over all possible j, but I will not iterate over all possible I. In other words, you are saying that you will still iterate over here, and for each j you will figure out how many valid i's are there. In other words, you are saying that how many x are there which are divisible by 2. In other words, you are saying that how many multiples of 2 are there in this array, and if you can figure out how many multiples of 2 are there in this array efficiently, you can solve this entire thing efficiently with m into some factor. That factor is how efficient you are able to count all the multiples of a particular number in this array nums1, right? So there are hence two different approaches, either go over all the multiples or go over all the factors. And by going over all the factors or all the multiples, I mean efficiently doing that. And we will be discussing both the approaches. Let's start with the second one, which is we want to, among n and m, we want to remove m, right? In other words, we are saying that we will iterate over all possible I. For each I will figure out how many valid j's are there, and I will count this in less than order m time. Now it's evident that we have to iterate over all possible factors of I, for factors of 8, right? So let's say if I is this, then you are iterating over all possible factors of 8. So possible factors of 8 is 1, 2, 4 and 8, right? Don't worry about how to enumerate this factor, we'll come to that. But let's say you have enumerated this factor. Now once you have enumerated this factor, you can simply iterate over all of these and count how many ones are there. So there is just one, so there will be one pair between 4 and whatever position that 1 is, in this case 1. So 4 comma 1 is a valid pair. Now how many 2s are there? There are 2 2s. So 4 comma 0, 4 comma 2 are valid pairs. So there are 2 more valid pairs we got. How many 4s are there? There is 1 4. So we got 1 more valid pair. How many 8s are there? There is 1 8. So we got 1 more valid pair. So overall we got 5 valid pairs for this particular I. In the same fashion, you will figure out the valid pair for all possible I, sum them up, and that will be your answer. Now, what is the overall time complexity? Firstly, you are iterating over all possible I. So you are doing something for n number of times. Now what you are doing, you are first enumerating the factors. So let's say you are enumerating the factor in order f time. We'll calculate f separately. Now what you are doing, you will get some number of factors. How many factors you will get? I'm not sure. For now, let's say nf, which is the number of elements in this factor. Now for each element, what you're doing, you're counting the number of occurrence of that particular element. So this counting, you don't need to go over the entire array. You can simply maintain a hash map, because this entire array is fixed from the beginning. So you can simply maintain a hash map and do this count in order one time. So after iterating over each of these factors, you are doing some order one operation. So let's forget about this. So you are saying that this will be your overall time complexity, which is the time to find out all the factors multiplied by number of factors we got, right? So how to factorize, we'll come to that. That's a very standard problem, but we'll come to that. How many number of factors are there? If you think about it, 8 has 4 as a factor, 8 as a factor, so it might look like number of factors can go up to order n, but that's not true. Number of factors can only be 2 root n at max. Now how we will come to that? So if number of factors is 2 root n at max, so this entire thing is 2 root n, or 2 root e, let's say n is already there, so e is the like element for which we are trying to find out the factor for. So 2 root e is nf. So root e is something we can afford because element is just 10 power 6, so root e would be 10 power 3, so 2 root e is fine. Now plus f, which is basically how to find out all these factors. So that factorization also you can do it order root e time, right? How we look at it, so this entire thing also you can do it in order e time. So this is root e, this is also order root e, so entire complexity would simply be n root e, which is sufficient to pass the given time constraint, right? So now we have two things to figure out. First, how to figure out all the factors, and second and more important thing is how you can prove that there are just root e or 2 root e number of factors at max. So I would encourage you to pause and try to think this two problem by yourself. So hope you thought about it. The answer lies in the fact that factors appear pairwise. So let's talk about factors of 42, right? If you talk about factors of 42, these are the factors of 42: 1, 2, 3, 6, 7, 14, 21, 42. Now if you look at it closely, they occur in pairs. So if you have 1, then 42 by 1 is another factor. Similarly, if you have 2, then 42 by 2, which is 21, is another factor. Similarly, if you have 3, then 42 by 3, which is 14, is another factor, and so on and so forth. And that is like obvious because this is nothing but a combination of some prime numbers. So let's say it is p1 cross p2 cross p3, some multiplied by something, right? Now if you take a few primes in the first factor, rest of the prime will surely be another factor, and that value would simply be 42 divided by whatever you have taken, right? So that's the basic math behind this entire thing. So now you are saying that we will have a mirror image, kind of mirror image of one factor with the other. So if we can figure out how many numbers are there here, we can simply multiply by 2 to get how many numbers are there here, right? Now we need to figure out what is the best, or what is the worst case number which we can, worst case count which we can have in the left side. So what we are having is, if we have x here, we have 42 by x here, right? So what can happen at max? A time will come when x and 42 by x will collide, right? So in that case, x will be equals to 42 by x. In other words, x would be equals to root of 42, right? And this is like the scenario where x is completely here, but if x is before that, then you will have 42 by x afterwards, and so on and so forth. So basically the worst case which x can go up to is simply root 42, which in turn means that number of elements in the left side can at max be root 42, which in turn also mean that number of elements in the right side will also be root 42. which proves the fact that number of factors that we have is simply 2 root e, where e is the number of a is the value of the element we are looking at. So we proved NF. Now is the time to prove how to figure out the factor efficiently. We don't want to iterate over everything from 1 to e, right? So you have to enumerate 1, 2, 3, 6, 7, 14 and other things. So enumerating the right side you can avoid. Why? Because if you have enumerated the left side, you can iterate over this entire thing again to enumerate the right side. For example, if you have 1, 2, 3, 6, you can iterate over this entire 1, 2, 3, 6 again, divide by 42 this time. So 42 by 1, 42 by 2, 42 by 3, 42 by 6, and you will get these 4 numbers as well. So let's figure out how to get all these numbers 1, 2, 3 and 6. Again, time to pause and think. So the simple solution is, you know that there can be root x number only, right? Or this entire value can go up to root x, right? And because root 42 or root e, so because it can go only up to root 42, why even bother about figuring out these values efficiently? Let's just iterate over everything from 1 to root 42 and figure out how many of them is divisible by 42. For in this example, if you have to figure out the value for factors for root 42, you will simply go from 1 all the way up to root 42, which is in this case is around 6 point something, which is 6. So if you go from 1 to 6, you can simply figure out how many of them are valid factors. So let's go over 1. So 1 is a valid factor because 42 is divisible by 1. Let's try 2. 2 is divisible by 42 is divisible by 2. So 2 is also a valid factor. Similarly, 3 is also a valid factor. 4 will not be a valid factor because 42 is not divisible by 4. So 4 is not a valid factor. Now 5 is again not a valid factor for the same reason. 6 is a valid factor. And now we'll stop because that's what we wanted to iterate upon. So from 1 to 6, we got these 4 numbers. And we are sure that we will not get any other numbers. Whatever number we get afterwards will be on the right side. So let's stop here and then simply iterate over the entire thing again to get everything in the right side as well. So to figure out 1, 2, 3, 6, what you have done is simply iterated over all the numbers from 1 up till root 42, which in turn means root e. So this factorization is something you can also do in root e time. So overall complexity is root e plus 2 root e, which is amortized to n root e itself, right? So this is the overall complexity of your algorithm. Just to reiterate what to do, let's get rid of all of these and let's try to dry run this for this I. So for 8, we want to figure out all possible j's that are valid. So what we will do, we'll first factorize it. Now how to factorize this? We will go from 1 to root 8. What is root 8? Root 8 is 2 point something, which is 2 if you downcast it. So what we want all possible factors of 8. We know that the middle element can go only up to 2. So let's try out 1 and 2 and see if they are valid. So 1 is valid because 8 is divisible by 1. 2 is also valid because 8 is divisible by 2. Now we will not try 3, 4 and anything after that because we know that this is the maximum limit of the left side, and whatever on the right side, whatever will occur on the right side, we can simply figure out from the left side itself. So we will simply say that with 2 we will get 4 and with 1 we will get 8. So these are the 4 factors of 8. How much time it take? It just take root e time because we iterated from 1 to e twice, 1 to root e twice. Now after we have figured out these 1, 2, 4, 8, we now need to count the number of frequency of each of the elements in the second array, and that you can simply do with a hash map and by just iterating over this again. And if you figure out the frequency of 1 would be 1, frequency of 2 would be 2, there are 2 2's here, right? Frequency of 4 would be 1 and frequency of 8 would be 1 as well. So overall you'll get 5 different pairs for this particular I, and that will be your answer for this particular I. Similarly, we do this for all the I and sum them up to get the answer, right? So this is how you will solve it. If you have paused to this point, strongly encourage you to pause and try to code this entire thing by yourself. Note that we haven't taken up K yet, so this is again one of the opportunity where you can pause and try to incorporate K into this solution by yourself. Incorporating K would be very easy, and we'll be discussing towards the end of the video. So pause and try to code this entire thing by yourself. Even without K is fine. So next, let's look at the second approach. Notice we had two approach. First by avoiding M and taking N. Second by avoiding N and taking M. So let's focus on the second approach, which means that we'll have to iterate over the multiples now. What does it mean? It means that we are iterating over all possible J. Now for each J, we want how many valid I's are there. In other words, we are saying that how many numbers are there which are divisible by some nums of J. For this, let's say nums of J is this 0, which is 2. So how many numbers are there which are divisible by 2, or how many numbers in this array are there which are divisible by 2. And how to figure out that? You can simply iterate over the multiples of 2 and count their frequency here, right? So let's do that. So first of all, you will iterate over multiples of 2. You will start with 2, you will go to 4, 6, 8, 10, and so on and so forth, right? Now for each of them, you will figure out their frequency. So first of all, how long will you go? You will go only up till E. After E, you will not go, because you know that that's the maximum element in this array, right? So this up till E, you will go over all the multiples, and for each of them, you will figure out the frequency. So how many 2's are there? That you can simply figure out using a hash map. So how many 2's are there? There are 2 2's. So there will be 2 valid values here. How many 4's are there? There is 1 4, so there is 1 valid value again. How many 6 are there? There is no 6, so 0 pair with 6. How many 8's are there? There is 1 8, so 1 pair with 8. And how many 10's are there? 0 2, 0 10. So overall you got 2 plus 1 plus 1, which is 4. 4 pairs with this J, right? Similarly, we'll do this for this J, and so on and so forth to get the final answer. Now, what is the overall time complexity of the entire approach? So what you are doing? You are simply doing something for each of the J, right? So you are doing something for m number of times. Now what is this something? You are first figuring out all possible multiples. So how many multiples are there for an element, like all the way up to E by whatever element you are looking at, which is, let's say, E dash or nums of J in this scenario, right? So that's the number of elements you are looking at. Plus, after you figure out each of these elements, you are again iterating over all these elements to figure out their frequency. So you are again iterating over all these elements to figure out their frequencies. So overall complexity is simply m cross multiple of multiples of nums of J, nums 2 of J, right? Now if you look at what is the worst case value for this expression, if you figure out the worst case value, that would be even worse than n cross m. How? Because this empty can go all the way up to E. Let's say everything is 1 here, right? Now what you are doing, for each of these elements, you are iterating over all possible multiples. So you, for 1, you are iterating 1 2 3 4 all the way up to E. Similarly, for this one, you will again iterate over 1 2 3 4 all the way up to E, and so on and so forth. So in this scenario, the complexity would simply be order n into E, and E was greater than m. If you look at E is 10 power 6, m was 10 power 5. So E was even greater than m. So this complexity is even worse than what you had with the brute force, right? So you have to optimize this for sure. Now how to optimize this? From here to the final solution, it's just one step, and I would strongly encourage you to pause and try to think about that step by yourself. So the why this n into e is coming? This is coming because for 1 you are finding out the value multiple number of times, but is that required? The answer is no. Why? So let's figure out that. You are figuring out valid I comma j pairs, right? Let's say for a hypothetical array, forget about what you have with forget about what you have with the current version. Let's just focus on what are the values. So let's say it is 2 comma 0, 3 comma 0, 4 comma 0. Again, don't look at this array. This is, let's say this is a valid pair for j equals 0, right? Now if it is a valid pair for j equals 0, it means there is a number which will divide by 2, which is divisible by 2, or there are 3 numbers which are divisible by 2, first at index 2, second at index 3, third at index 4. Now if you take j equals 2, then also there should be these 3 numbers which should divide 2, because this value is not changing across these 2 indexes, and hence the number which should divisible by 2 will also not change. So overall you will get exact same pairs, right? So if you have figured out those pair here, why are you reworking the same at this index? And that's exactly we want to avoid, and if we do that, the complexity will reduce a lot, and you will see the magic now. So let's do one thing. Let's figure out the frequency of each of the elements, and we will do the work exactly once for every element and just multiply the frequency there to get the contribution across all possible occurrences. So for this scenario, we have 1 1, we have 2 2s, we have 1 3, we have 1 4, 1 5, 1 okay, 6 is not, 1 6 is also there, 7 is not there, we have 1 8, and 9 is not there. So this is the frequency. Now we are saying that we will go over the multiples of 1 exactly once, we'll go over multiples of 2 exactly once, we'll go over multiples of 3 exactly once, we'll go over multiples of 4 exactly once, and so on and so forth. Now what will be the overall complexity? So for this you are going over all the multiples of 1, that will take you order e time, or order e by 1. Now for this you are going over all the multiples of 2 exactly once, that will take you order e by 2. For this you are going over all the multiples of 3 exactly once, so e by 3. Similarly for this it will be e by 4, and you will be doing this entire thing until e by e, which will be the last element of this series, right? And this will be your overall time complexity as well, right? Notice that we are not multiplying m now because we have considered the work for each iteration separately, right? So this is the overall complexity. Now what this value will be amortized to? Let's this is a very simple math that you might have done in 11 or 12, so try to pause and try to think about that by yourself. The answer is simply e log e, right? And this is like log e, not log 2e. Now why I would leave that to you, it basically comes from the fact that you can do integration over 1 over x. So this function is just simply like take e as common, and this is 1 by 1, 1 by 2, 1 by 3, all the way up to 1 by e. So this is 1 over x, you can integrate from 1 to e, and if you like do this integration, it will be log of x or ln of x, and ln of e minus ln of 1. Ln of 1 is 0, so ln of 1 is not 0, it is constant, but we got ln of e overall, so e multiplied by ln of e is particular complexity. So if you do this entire thing can be solved in e ln e. E is 10 power 6, and ln e would be smaller as well, so this complexity should pass. But if it doesn't pass, you can simply skip over 0 elements, and this e would simply be reduced to m, like in very naive fashion, not exactly, but overall it is reduced to m. So e ln e would become around m ln e, that was even smaller, and that should pass for sure, right? So these are the two approaches that I wanted to discuss. If you have any doubts in any of the two approaches, feel free to comment in the comment section below. But before doing that, I would strongly encourage you to at least try to code this entire thing, or at least try this with pen and paper if any of the things is not there after rewatching that section. So till now we have been avoiding k altogether, but the problem talks about k as well, right? So how to incorporate k? One of the simple way to incorporate k would be just divide everything here by k, or in other words, like you wanted in this particular approach, you are iterating over all the elements here and then figuring out how many counts are present here. So if you multiply everything by k here, that is one of the approach. But if you multiply everything by k here, this e will go up to 10 power 8. So either you can 10 power 9. So either you can keep a hash map instead of an array here, or you can simply divide by k for each of these elements. Both of them is fine, and the same approach you can do for this part as well, right? So adding k into the expression is very easy. So with that, I would encourage you to pause and try to code. Next we'll be looking at the code. So I will be showing you the code for this approach because this was not that obvious. So I will be showing you the code for this. The other one you can code by yourself. So the code is very straightforward. We simply have two frequency array, one frequency which goes over all the elements for the first array and count for I by k. Why I by k? Because we want everything to be divisible by nums2 of j cross k. So if the number itself is not divisible by k, it will not be divisible by nums of 2 j cross k as well. So for every number that is not divisible by k, I have completely skipped that, and if the number is divisible by k, I will simply take the residual, and that will be my number that should divide nums of 2 of j, right? So this is the frequency of all the elements in the first array. This is the frequency of all the elements in the second array. Now as we discussed, we will go over all the frequency from the second array, and for each of them iterate over all its multiple. So we start from 1, go all the way up to n. If count 2 of I is 0, let's continue. Otherwise we want a sum of frequency of all the multiples from the first array. So we iterate over all the multiples, like j equals I, j less than n, j plus barabar I. Now for each of these we take the sum across the first array frequency, and this already taken into account k as well, so we don't need to worry about k for now. So after this we got how many numbers are there which are divisible by 1, or nums of j in general, and how many numbers are there which has the same value is something which we have in this frequency array. So we can simply multiply these two to get the total contribution of this number itself, and we'll sum them all for every possible j and we'll get the answer, right? So in the same fashion you can do the code for first one as well. The only thing that differs is you will now be iterating over factors instead of multiples, right? And you don't need the second array as well, second frequency array as well, because here you don't need to optimize for iteration over this array as well, unlike the other approach, right? So if you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.